Okay, so in the last lecture, we learned about the basics of neural networks and how do we backpropagate the errors to each weight parameters we are learning in the model. And today, we are going to learn different type of neural networks, convolutional neural networks, or CNN for short. So in the last lecture, we learned fully connected layer. We call this as neural networks, but we call this is another term of this, which is fully connected layer. Why? We have value x, the values in the x in the input data, and it maps to the output values in this course. And we have the weights, which connects, which represent the relationship between xi and si, which is in the shape of C times D, where the C is the dimensionality of S, D is the dimensionality of input. And we also learned that we can represent like this, which is each edge represent the weights applied to each input value to output value. We call this as fully connected because all of these edges are connected. Any pair of input value and output value are connected as with an edge, and they will have some weights, even if it's 0. So that's why we call this fully connected layer. So we can represent this as a vector like this. So we have D values in W. We have D values in X, which is here. And we have the same number of weights in one of those W, so one row of each W. We take the inner product between them, or vector-to-vector multiplication, which is inner product, and it outputs one scalar value, which is this value. And we have two of them here. So the second one will be the second row of this W, and we do the same thing. Take the dot product, and we will have another scalar, which is here, right? So yeah, it's here. We have suppose we have 5 output values, then each weight can be represented like this. So all the edges connected from all the input values to the first one, which is here in the first row, and all the edges connected to the second output, it's in the second one, and so on. So the shape is like this: C times D, and this is D, so it's multiplied, so output is C times 1. So that's fully connected layer we have learned in the last lecture. And now let's think about an image. So in image, we have pixels arranged in 2-dimensional matrix like this. So if we build some fully connected layer, that will look like this. Each of these values are multiplied with some weight value in each of these edges, and they are all multiplied, which corresponds to taking the dot product between these two vectors, and then we will have some one output value. And they are so what we do in the inner product is this: we multiply scalar values correspond to the same location, same index, and then we sum over all of those multiplied results. And that's the definition of inner product, right? So we exactly do the same thing. Each input value or each input pixel value is multiplied with some weight values corresponding to that pixel, and we sum over all of them, then we will have some output. So this is just a 2-dimensional version of the fully connected layer, but as some students asked before, we just flatten this to this, this blue one, and then these are the same number of weight values, and we take the inner product like that, and then we will have the output value. So still, we are fully connected. This is fully connected layer, but just input values are arranged in 2-dimensional space. Now, let's think about something different. What we would like to do is recognizing some pattern or object in some image. Suppose we would like to build some filter to detect human eye. So we would like to design some filter that gives high score where the desired pattern, which is eye, matches in the image. And we usually don't know those eyes, how big those eyes are, or where they are. So they can be in the middle like that, or on the right, or at some corners, or how many of them are there, or how big it is like this. It can be big like this, or it can be small like this. We don't know that, right? So what we do is we define some filter which roughly matches to the shape of eye, and compute the scores, the matched scores, and we find where it is, where it gives the highest value. So previously, human eyes were detected by some filters like this. So white, black, and white. So that's the general pattern, rough pattern of human eye, right? So we prepare some filters like this, multiple numbers with different sizes. And we scan over from here. We check if his eye is here by multiplying this value. So these are kind of weight values like here. So we compute dot products with the values in the image and with the filter values, and sum all of that. And if they match, then we will have high score. Otherwise, it will be small score, because these are resembling the human eye shape. So we just move around all the possible positions in the image, and we will figure out that if we put that filter around here, we will have high score, or here. And for this one, these small ones will not work really well. But if we use this large one, then we will have high score. It's something like this was used previously in computer vision to recognize something. Human eye is easier because it has very clear pattern of white, black, and white. But how can you find out where a computer is, or where a cat is, or something like more complex shaped, or some objects or classes? Then how can you design these filters? What should be the shape of those filters? So that is something that we are going to learn from now on. So previously we have human design. These filters were designed by human intuition, but how can we learn from the data? That's the essence of the deep learning and machine learning. So this is how can we implement what I just told? So we are given an image, which is this image, and we are given a filter. Suppose we are given a filter. We are going to learn what filter to use later, but suppose they are given like this. So like 110011, 110011, some patterns like that, and some threshold. When we multiply these filters in all possible positions of this image, and each pixel will give the output score for each location. And if that is above the threshold, which we define, then it fires. OK, I is there. So we can output like that. So that is called convolution. And that can be implemented using up to 4 nested loops. But that's slower. So you can vectorize your implementation to reduce the number of nested loops, and that will be faster. So I usually ask the students to do this during the class and check their codes. But we don't have that much enough time this semester, so I'll leave this as a homework. So this will be not part of this homework 1, but I encourage you to do by yourself, because this is something easy in concept, but when you actually try to implement, that will be a little bit challenging, but not really hard. And actually, this was the interview question that I was asked when I was interviewing with NVIDIA. NVIDIA is one of the prestigious company and doing a lot of good research. And when they hire a research scientist, they ask this question: can you code this? So yeah, I had to code this in the whiteboard. So yeah, they do actually ask a question like this. So please do practice. So let's move on. So we have the spatial locality. So we talked about spatial locality. So how can we design a good filters? We just saw some example of the human eyes, but in machine learning, this is the philosophy of machine learning I told before. We design only the overall architecture only, and parameter values are just randomly initialized, and we fit them using the data. That's our philosophy in machine learning. This machine learning is part of AI, which use data-driven approach. So in this case, the architecture, we would like to preserve spatial locality. Why? When we would like to recognize something in the image, something like human eye, we know that that's discoverable only when we look at some small portion of the image, not the entire part. So when something is there, we don't have to look at the entire picture, but the decision mostly affected by the nearby pixels only. And the nearby may be just very small. For very small objects, it can be just a few pixels, or for bigger images, maybe it's larger, but still its nearby pixels are important. So that's the spatial locality. So main assumptions with convolutional neural networks are two things. Spatial locality means each filter looks at only nearby pixels. So that means the observation of some objects we would like to discover from the image is determined only by the nearby pixels, but not far away. That's one assumption. Another assumption is that positional invariance, the same filters are applied to all locations in the image. Right. In this example, human eye can be appearing in any place within the image, but the shape is roughly the same wherever they are located, right? So that's why we were able to apply the same filters to discover where it is. So these are two assumptions, spatial locality and positional invariance. So we look at only the nearby pixels, and we do that for all the possible locations in the image to find out where we have highest score. So that's the main assumption of convolutional neural networks. But that's valid for all kinds of image, which means when we do some object recognition for all possible image recognition tasks. So maybe not, something like this. So this is an application of object recognition to some medical stuff. We take a chest X-ray, and the doctors try to locate what happens, what issues this patient potentially has by looking at this picture. So we may use some computer vision techniques to discover some patterns, what doctors are looking for. And that's actually working really well. But in that case, we have some domain knowledge that, for example, lung cancer can happen only in the lung. And in the case of chest X-ray, the location of lung is always fixed. So it does not happen in the edge of these images. They always take the X-rays at the same position. They move human, not the camera, to have the exactly same location of human body. So something we would like to discover, like cancer, happens always in the limited positions. So we don't actually have to check the location of these filters in all the places. But that's just a special example. In most cases, positional invariance is actually valid. So let's move on to actually look at how convolutional layer works. So suppose we have very simple case, monotone image. This is black and white image of size 32 by 32. So width is 32, height is 32, and we have one channel, which is monotone. Okay, so each pixel is represented by one value, one intensity value. And suppose we have 3 by 3 filter. What we would like to discover is some pattern appearing in 3 by 3 patch, like this. So convolutional layer does convolve the filter with the image, which means slide over the image spatially and computing dot products, which is we start from here, 1 to 3 and 1 to 3, this part. And we will have 9 values in the image on that part. And we will have 9, we also have 9 values in this filter. So they multiply element twice, and we sum all of them. So that's the dot product, right? So that score corresponds to how much this part of image matches with this filter. So if we have higher score, then this filter is a good match there. And we move this filter around this image to compute that score in different locations. That's what we are doing with convolutional layer. Something like this. We suppose we are doing that in this position. Then we have 9 values in this filter. So each of those corresponding values are multiplied. And then we sum all of them. And we call this as activation. A score how much this area matches to the filter. So this is activation score. And we do this in multiple positions. So in the next position, we do exactly the same thing. And we have another activation score. And we repeat that. So we will have also two-dimensional shape of this image having these activation scores. What if we have color images instead of monotone? Now we have same size of image, but the number of channels are 3, which is RGB. So each of these channel has some integer scores, integer intensity values in each pixel. And with all of those 3, we represent it as a color. So this is what machine views as an image. So it's 32 by 32 by 3 tensor, which is the image representation for the computer. Here, we would like to have some same size filter, but because we have 3 channels, we need to have 3 channels in the filters too. So the first 10 seconds 3 means the shape of this. This is 3 by 3 width and height, and 3 is the number of channels here. We do exactly the same thing. Slide over the image spatially, computing dot products. So it looks scary, but still it's the same. We have 3 channels, and each of them are same as before. So we have 9 values in each channel and filter. So we multiply them element-wise and then sum over that. And we do that for R, G, and B separately. And then we sum all of them together, which is, in total, we have 3 times 3 times 3 filters. So these 27 numbers are what we are going to learn using the model. These values in the image is given as input. Always keep that in mind. Image is the input, so they are fixed. And the values in the filter is what we are learning. So they are initially randomly initialized, and they are updated using gradient descent or something else to optimize to the data set, to the task. But here, these values are what we are learning. So that is the important part. We are learning the values within these filters. That corresponds to the weight in the linear models. But here, remember that we always had one additional terms, which is bias, right? In the linear classifier, we added the bias term, but we didn't explicitly always write that because we can always add it to as a part of the weights as the last row. So we usually skip this because this is we usually have much larger number of filters, and this is just one, so we usually don't write it or draw it, but actually we always have it in our model. Because, again, what is the bias? We would like to model dataset independent pattern, so which usually lies only in the label side. So we always have this bias term in our model. So we have 27 filter values plus 1. So in this model, we have 28 numbers to learn. Okay. So this one shows how convolution layer actually works. So convolution over entire image, we start with the very left and top of the image, apply this convolution, and we will have one output value. And we do that on the next, we move it to the right just by 1 pixel and do the same thing until the end of the width, at the end of the image. So we have here with 4 output values. And we do that the same thing in the next row. And we do all the rest possible positions, then we will have some activation map like this. So question. We have 32 times 32 times 3 channels image. And the shape of this small filter is 5 times 5 times 3. And then what is the size of this output activation map? I'll give you 15 seconds to compute this, and we'll ask. Okay, Michael is here.
Yes, I am.
Yes. What's the output size?
It should be 28 by 28 by 1.
Okay, can you explain why? It's correct.
Yeah, because we only apply the convolutional filter in positions where all 25 values, 25, you know, in X and Y direction, can be matched to pixels in the image. So we lose 2 positions in every direction in X and Y. And then there will be 1 value for each of those positions.
Yeah. Okay. Yeah, thanks for your answer. Is it clear to everyone? Okay, great. Now, we have done that just once. So if the output size was 28 by 28 by 1, we have one output map like that. But we can do that multiple times. Remember, in our linear classifier, one of the issues we had was we have just one template matching for each class. And we said that that was not a good thing. So in this model, we can actually have multiple patches like that, multiple activation maps. So we are actually doing exactly the same thing multiple times so that the model can learn multiple templates to match to each class. So same question, but slightly differently. For the same size of image, same size filters, but we have 4 of them. Then what is the size of output activation map? Kim Hyun-seok?
Yes.
Yeah, what would be the answer?
28 by 28 by 4?
Yes, exactly. So instead of 28 by 28 by 1, we have 4 of them. So input was 3 channel, but now we have 4 channeled outputs. Okay, great. Is this clear, everyone? Okay. So now we have another image of size 28 by 28 by 4. So this was input, and we have this output. But you see that this looks like an image, right? We had 32 by 32 by 3, which was 3 was RGB at the beginning. But now we have something else, but still, this is weight and height, and this is number of channel. So this is another kind of image. So which means we can do another convolution on top of this in a similar way. Okay, we take just this as an input, and we convolve over this space, and we will have another activation map. So we can stack convolution like this multiple times. So let's do this exercise again. On top of this image, which is the activation map, not real image, but activation maps, we apply another convolution, 10 filters of size 5 times 5 times 4. What is the output size? Let me give you 10 seconds, and we'll ask. Hwang Ye-jin?
Can you hear me?
Yes. Do you have an answer?
Yeah. It'll be 24 times 24 times 10.
24, 24, 10?
24, 24, 10.
Yes, right. So exactly the same way. So as I'll not ask why. So thanks. So yeah, the shape reduces from 28 to 24 because we're using the same size of patch, and because we have 10 of them, 10 filters, the shape like this. And we can apply another activation again and again after this to stack these convolutional neural nets. So why do we stack them? So what's the meaning of that? So here's why. We are given an image, and then we stack convolutions 3 or more times, and then we learn some classifier, and then we have this output. So backpropagation is from the back. So from this loss, we update the classifier, and then we would like to update these lower parts, high-level features. So the first, at the last level of these features, what are these? These are learned pattern from the data set, which are mostly useful to optimize the performance of this classifier. So from this machine's, this model's perspective, our goal is optimizing this model as much as possible, which means we would like to have the right class answer at the end, always, or as much as possible, which means this classifier needs to be optimized to that. And you may remember that this was the trainable classifier, but before than that, these were feature extraction. At the beginning of last lecture, we have seen that we have some deterministic function to extract some features, but can we automate it from learn from data? And that's what we're currently doing. So these features are learned from the data. So what this model needs to do, it has this fixed size of the capacity, which is this. In this model, it's something like this, 24 times 24 times 10. This is the number of values it can hold. This is the capacity. And it uses these numbers as much as efficient as possible to optimize the performance of this classifier using the gradient updates. So the meaning of this high-level features is most useful features to distinguish different classes in the data set. So in this data set, we can imagine that they may have some beehive or some birds or some eyes or probably some animal data set. We can conjecture because this one captures these as an useful features to distinguish if it's a bird or something else, or if it's beehive or something else, something like that. Then what will be the middle-level features? In the next level, these are the most useful patterns to learn or represent these high-level features. So they are simpler patterns, but they are actually part of these more complex high-level features. But they are more primitive, and when you learn these high-level features, we combine these somehow based on the data set to represent these high-level features. And same thing at the lower-level features. These are more primitive, which is usually just a color patterns or some edge lines. So we combine these to represent this eye, for example. To represent this eye, we need to have all direction of these edges or these color patterns, some orange and blue colors patterns. They can be used to represent some part with color change, something like that. So what we learn in the lower level features is more primitive like this. And at the higher levels, we have more distinguishable features for each class in the data set. So that's why we stack these convolutional layers multiple times to learn these intermediate features. If we have just a few layers, just one or two, then it's really hard to learn these useful features out of just pixels. That is closer to what we've done in linear classifier. And we said that we never use the pixel values directly to learn some classifier, right? That's why we stack these in a hierarchical way to learn the useful features hierarchically. Okay, so you have learned how convolutional neural networks work, and you can now build image recognition. But there are some more things you may need to know. So let me quickly go over that. So that's what we've done. We have 32 by 32, and we applied the filter, and this was the activation map we had in the previous one. Here are two questions. The size of the activation map, you see that they are shrinking in size, right? And you know why? Because we start from the first to the end, but because the size of the filter is not 1, it's larger than 1, we cannot have the same size of as the input. But if we do this, if we stack multiple layers from 32 to 28, 28 to 24, and 24 to 20, so if we stack like more than 10 times, then the image will disappear, which is then what we can do with that, right? So can we avoid this? We don't want to reduce the activation map size. And the second question is, if the input image in high resolution, like 4K resolution like this, if we compute this for all the possible locations, then the computation overhead will be super high. Do we really need to do that? So one solution may be just resizing the input image to very small size. But still, in that small size, do we really need to always move that by 1 pixel? So can we have any better way to deal with the large image? So these are the two topics we'd like to talk about now. So one idea is stride. We don't have to move always 1 by 1. So this is what we've done. 7 by 7 input, 3 by 3 filter, and what we've done is starting from here, the next position, and here. So we have 5 output values in the first row, and then in the second row, second, third, fourth row, we have the second output, and we repeat this until the last one. So we have 5 by 5 output activation map in this example. That's what we've done previously. Okay, but we can do that with stride of 2, which means we have the first one, then jump 2 pixels instead of 1, and another pixel after 2. And then to the row side, we also move by 2. So in this case, we have output of 3 by 3 instead of 5 by 5. So activation map shrinks even more. But if this input image is really huge, we don't have to move it pixel by pixel. Let's do this again with stride 3. First one starts here. Second one we get here. And then what should we do? The third one doesn't match. So this 7 by 7 input image and 3 by 3 filter with stride 3 doesn't fit. It's not valid. So we cannot apply 3 by 3 filters on 7 by 7 as is. So we now see that it's not always possible. Sometimes it has some problem, right? So here's the summary. Let's define the n is 7 here. That's the image size. We can just assume that always the width and height are the same for simplicity. And this is the filter size, f by f. Then output size is like this, n minus f divided by stride plus 1. So if that's an integer, then we will have valid output size. But otherwise, we will have some non-integer values like that, which means which is strange because images should be integer size times integer size. So this is weird. So what we do to avoid that is padding. So even if the input image is given as 7 by 7, we may add some virtual or additional pixels or rows or columns, and we just pad them with 0. There may be some other ways of padding this, but 0 padding is widely used. So let's do that. 7 by 7 input image and 3 by 3 filter, and we stride 1. Then, as we did before, it's like that. So we have 7 outputs here. Again, again, and again. Output size is 7 by 7. Oh, input was 7 by 7, but output is still the 7 by 7, right? That's what we wanted. Even though we stack this multiple times, the input and output shape will be exactly the same. So we don't need to worry about shrinking the size, right? So in this way, we can actually add the 0 padding to avoid that activation map shrinking problem. So here's another summary. If we apply padding, then the output size becomes like this. And minus f plus 2p, this p is the padding for each row or column. So here we applied all the same padding on the top down and left and right. So output shape looks like this. And if we set p is equal to f minus 1 divided by 2, then the map size will be always the same, which is preserved. So if filter is 3 by 3, padding is 1, 5 by 5, 5 by 5, then the padding is 2, and so on. In that way, we can preserve the original size of the input in the activation map. So with padding, we don't need to worry about these shrinking. So here's an example. So we have 32 times 32 times 3. That's the input image size. And we apply 10 filters of size 5 by 5. And we apply stride 1, and padding size is 2. What is the output size? And what is the number of parameters to learn? And we would like to compare the number of parameters if we implement this as a fully connected. So I will give you 30 seconds to compute this, and we'll ask. You, Uni, data science?
Yes.
Yeah, can you answer?
The upper size would be 32 by 32 by 10 of courses.
Yes. So because we applied the padding and stride as so that we can have the same size, the output size is 32 times 32, and the 10 came from the number of filters. So it's correct. Great. Okay, thanks, Uni. And Kyungsun, Kyungsun.
Yes, Professor.
Yes. What is the number of parameters we learn here?
We have 10 filters, so and each filter has 5 by 5 by 3 and plus 1 bias. So we need 10 by 76 parameters.
Yes, that's exactly correct. So really good job. So for those who are not following, the number of parameters is what we are learning in the model. I'm emphasizing this all the time. And what is the weight we are learning in this convolutional neural nets? That is in the filters, right? This image is given as input. They are fixed. What we are learning is this filter. And how many filters we have? We have 10 of them, right? So that's why we have 10 multiplied here. And within each feature, how many values we have? So we have 5 by 5. So it's 5 by 5. But in the input, we had 3 channels, which means, for example, it's RGB. Then in the previous slides of today's lecture, I showed that we always need to have the same number of filters, same number of channels in the filters, right? That's what we have multiplied 3 here. Because the input has the 3 channels, our filters also needs to have 3 channels. So 5 by 5 times 3, and this 1 is for the bias. Remember? So each filter has this number, 76 values to learn, and because we have 10 of them, it's 760. What if we do this fully connected? In fully connected, the input and output, all the values are connected by edge. and we counted number of edges. So this is really huge. So the input size was this, 32 times 32 times 3. Output size was 32 times 32 times 10. So we basically multiply all of them. But we also have the bias terms for each of these outputs. So we have this number, which you cannot compute without computer. But so compare this number against 760. Instead of this number, our model just needs to remember this small number of values, but still we can recognize the objects even better, actually. So how this was possible? Here's the thing. We at the beginning of this lecture, we mentioned that these are the two assumptions. Spatial locality, which means the size of this filter, 5 by 5, is much smaller than the entire image. And positional invariance, which means we don't have to remember the filters depending on different locations. We apply the same patch to everywhere. So we have just this one filter here. So thanks to the spatial locality and the positional invariance, the number of parameters we are learning dropped this significantly. And that's why convolutional neural nets is much more efficient than fully connected layers. And one more example before we finish. 32 by 32 by 3 input image. And now we are applying 6 filters of size 1 by 1. Let's try this one and no padding. What would be the output size? I'll give you 10 seconds. Kim Chang-hee from Mechanical Engineering. Chang-hee, are you here? Please check if your microphone is on. Okay. Okay. Yeah, he said that there's some error in the microphone, so you can answer in the text. Yeah. Okay, 32 by 32 by 6. So yeah, output size is preserved because we are just applying the convolution 1 by 1. Each pixel just uses the value inside that, and the shape is just preserved. And because we have 6 filters, the size is this. Okay, that's correct. Number of parameters, Hee-sung, Kim Hee-sung.
It's 24.
24. Okay, so because we have 1 by 1 filters, and this is the number of channels, and with the bias terms and multiplied by 6. So that's correct. Great. So some of you may ask that why do we 1 by 1? This does not reflect any spatial locality, right? We are just looking at it that pixel only. Can we recognize something out of just one pixel? So why do we do that? Here's the answer. Actually, I asked this question in the last semester's data science qualifying exam. So this is really important thing. Each filter performs 3-dimensional dot products, which is not just the rows and columns, but column-wise, the channel-wise, we have multiple channels, right? RGB or activation maps from different channels. We take the dot products in that direction as well. So even if we do that 1 by 1, still we have multiple values channel-wise. Those channel-wise values are mixed to output in the new activation map. So this can be applied to reduce the dimensionality in most cases. Suppose we have 32 times 32 times 1000, and we would like to reduce the dimensionality or the number of channels to 50. Then what we can do, you may use some fully connected layers, but that's too inefficient. We would like to still have the spatial locality. So you don't touch pixels, different pixels, but inside each same pixel, you just compute the fully connected layers from 1,000 values to 50 values by using this one-by-one convolution. That's really widely used. And in the reading material, we have some more detailed explanation about that. So I encourage you to read that. So yeah, here's the summary. Okay, it's 3 minutes over, but yeah, let me quickly just finish. So in the convolutional layers, we need to define these 4 things. Number of filters, how many filters we are going to have, number of channels, and filter size, which was like 3 by 3 or 5 by 5, and the stride size, how many pixels we would like to jump, and how many zero padding we are going to apply. So these 4 things, K, F, S, P. And given these 4, the shape of the convolutional layers are defined, well defined. And these are the formula for the output pixels, output activation map size, and the number of parameters to learn. So this is just summary size. So please, you don't have to memorize all of these things, but just understand why that's working like that. And remembering this formula may be sometimes useful, but I don't require to memorize all of these. And these are the TensorFlow API. So I'm just showing that these are exactly requiring the 4 things we have just shown. So number of parameters, which is filters, and filter size, or it used the term corner, but it's basically the same thing. Corner size, strides, and padding. Padding, here's the interesting thing. They use same or valid. So if you just put valid, then it doesn't use any padding. Or if you just type same here, then it automatically computes what number of paddings is actually needed to keep the same shape. So it works like that. So here, the input shape is like this. You have 28 by 28 by 3, and this is the number of images, 4 images. So convolutional 2D layer with 2, which is the number of filters, and 3 is the corner size, so it's a 3 by 3. And the others are just by default. So stride is 1, padding is valid. So because the padding is valid, the output size actually changes. Still 4 images, but it's 26 by 26. And because the number of filters was 2, it's 2 here. But if you change the valid to same here, then the shape has changed to 28 by 28. So try to check if this output size is correct and why they are like that. Please try to review and understand. And okay, yeah, this is a very last slide. So fully connected versus conv. Convolutional layer is a special case of fully connected layer. How? In the fully connected layer, we had the edges connecting all possible combinations of input and output values. Remember that? In the convolution, we are shrinking that to looking at only the nearby pixels, and we apply the same operations all over the same places, which is a subset of the entire all possible connections, right? So in that convolutional layer is a special case of fully connected, which is, we have seen that in our previous slides. We have reduced this number of large operations, which reduced to the 760. But this is actually shippers strict subset of this large number of possible connections. So that is the summary. And we also have some more details about these things in the reading materials. And I actually asked 2 questions about this in the last year's qualifying exam. So if you are GSDS students, I strongly encourage you to review this very thoroughly. So yeah, we are 7 minutes over. So thanks for your attention. And next time, we are going to quickly finish this pooling layer and move on to training neural networks. Thanks for your attention.